Hey guys, welcome back. In this video we're going to consider examples 1 and 2 from your magnetism notes packet. So it needs a lot of practice to get correct answers consistently using the right hand rule. So it's important that you actually practice these. So don't just watch me do it. You should already have seen my first video on the right hand rule and should approximately know kind of how it works. And so what you should do for all of these is try it out on your own and then see my explanation, see my answer. Okay, now, remember the way this works is your hand points in the direction of the velocity. Your fingers point in the direction of the magnetic field. If it's like this, right, where you've got V and B perpendicular to each other, there's going to be some kind of a force. If V and B are parallel, the force is 0. And then your thumb is the direction of the force. So your hand really should be like this at all times. And then the goal is to kind of match it up so that they work out. Okay? So if you can get V and B to point in the direction of the whatever those things say, then your thumb will point in the direction of the force. Okay, so first one, we've got a proton moving north, enters an eastward directed magnetic field. Now, I don't know which way your screen's oriented, but for our purposes, we will try not to use cardinal directions. And I'm going to have north-south be like this on the screen, okay? All right, and then let's see if I can get east and west in the right places. Okay, there we go. So for our purposes, north, south, east, west are directions on the page, okay? All right, so let's see. We've got a proton. It says moving north. That would be that way. All right, enters an eastward directed magnetic field. My finger, aha, I've got it. So now my fingers, which are the magnetic field, remember, point this way. Okay, so a couple of things that you may not do. Don't bend your wrist, okay? Oh, I got it. No, don't bend your wrist. Don't do it. Your wrist has to stay rigid, okay? Your fingers only have one joint for this law. That's right here, okay? If you're bending these, no, you're doing it wrong, okay? So, north directed, the magnetic field was to the east, and my thumb, you can tell, is going into the page. Well, that would be, in terms of absolute directions, down, okay? So the correct answer for part A is down. All right, now if that did not make perfect sense to you, review back over that part of the video and see if you can puzzle that one out. Okay? All right, a proton moving vertically upward enters a magnetic field directed vertically downward. All right, now let's see. Vertically upward would be towards the camera, so this is a little tricky to operate here. All right, there we go. V is going straight towards the camera, and the magnetic field is going straight down. My fingers don't... if you get something where you're like, I don't think that's physically possible, then the answer is probably 0. And this would be in keeping with what we said last time about the QVB sine theta and the necessity of V and B being at least a little bit perpendicular in order for there to be any force. If you have V and B like that, or like this, then the force is 0. So the correct answer for part B here is 0. There is no force. All right, let's consider C now. A stationary, stationary? That means it's not moving. Well, that's an easy one also. The correct answer is 0. There is no force. Okay, so if it says it's not moving, then there isn't a direction for the force. The force is 0. All right, so let's see, D. All right, this one is tricky. I'm not going to warn you any more than that, but it is a little tricky. All right, so let's see. An electron moving south enters a magnetic field directed vertically upward. All right, well, south would be that way, down the paper. Vertically upward would be this way towards you, so I'll have to turn my hand over so that my fingers can... Okay, so it looks like my thumb is trying to point west. And the correct answer is, therefore, east. What? Why is it east? Well, the reason it's east is because it said it was an electron. Electrons are negatively charged, which means that you reverse all of your answers. So whichever way a proton would go, that's the opposite of the way that an electron would go. Okay, so I had southwards velocity. I had a field vertically upward. Okay, and that, using the right-hand rule, gave me a force to the west, but I have to reverse the answer because it was an electron, and therefore it goes in the opposite direction. Great. All right, now, example 2. If we have an electron in a magnetic field like this, moving, it says, to the right. What this example is trying to point out to us is that the direction of the force on a moving charge doesn't remain constant. Because after all, if it's experiencing a force, well then, it must be accelerating. And therefore that means it will have a change in velocity. If it has a change in velocity, then that must mean that there will be a future change in force, since its velocity determines the force. The direction of the velocity changes the force. So if its direction changes, the direction of the force changes as well. All right, so if it's moving to the right, let's see, using my right-hand rule, there's the velocity. That is an into the page magnetic field, so my fingers will curl this way, and my thumb points up the page. So the answer is down the page. What? Because it's an electron. Okay, so the initial direction of the force is going to be down the page. I guess I'll use, I'm screwing up my color coding here, but I need a different direction to indicate force versus velocity. So there we go. All right. Now, if that's the direction of the force, a little while later, instead of it being moving this way, it'll be moving, say, that way. Okay. All right, well, when its velocity is that way, if we do our right-hand rule again, faithfully, right, we'll have V is that way, B is into the page. So that means the force will be, again, I got to switch my answer. It won't be in the that-away direction like my thumb was showing. It'll be that way. All right, now if you are being clever here, you can probably guess already what's going to end up happening. If not, keep watching. Or even if so, keep watching. All right, so a little while later, it might be moving, say, straight down. If I do my right-hand rule again, what I'm going to end up with is the force will be, once again, perpendicular to that, directed that way. Surely by now you can see where this is going. What will happen is the electron will move in a circular path. That's a very crappy circle. Just squint, use your imagination. Because no matter what direction its velocity happens to point in at a particular moment, the force is going to continue to be perpendicular to that velocity. So when it's here, the velocity will point, or the force will point that way. When it's here, the force will point that way, etc. And the result is going to be that it will move in a circle. All right, now charges don't always move in circles. Sometimes they move in, semicircles, but it's always some sort of a circular arc, some portion of a circle. All right, now, how would our answers have been different if the particle had been positive? Well, everything would have been switched around, but we would have gotten a circle up this way, okay? Although, actually, specifically, it says it's a proton. So there's a couple of differences, and we're going to get into the math of this in a little bit, but actually the size of the circle that the thing makes is related to a couple of things. It's obviously related to all these, but it's also related to the mass of the particle. So we'll get into that in a slightly later video, but for a proton, it would move up this way, but also it would move in a much, much larger circle. like 1,836 times larger. Okay, I think that's enough for you to be able to do your homework. All of the homework is right-hand rule stuff. So it should be just application of this sort of a thing, all right? You probably don't need to decorate your hand, okay? But what you do need to do when you're doing right-hand rule is make sure that your hand is like this, and that, of course, it's your right hand, okay? So as long as you can orient everything in the direction that it's describing, you should be able to answer the problem. If things are in such a way that you're like, I can't even get my wrist like, then turn the paper, and it should be possible then for you to contort your hand into the necessary directions. Thanks for watching.